So I'm going to take something that generates a voltage. Could be a sensor, could be some other circuit, could be a function generator, and I'm going to represent it by its Thevenin equivalent circuit. So I'm going to have a V in and an associated series resistance. And then I'm going to connect this to an op-amp, but I'm going to connect it in a different way to what we did before. So you might remember when we studied the inverting circuit, we connected our input to the negative terminal. But now I'm going to connect it to the positive terminal, and we're going to see what impact that has on our actual circuit. Now, to complete this design, I obviously need to provide a negative feedback path. So a negative feedback path means that I need to take the output and run it through a resistor and then bring that in to this negative terminal. So this would be our feedback resistor. But remember that ideal op-amp has absolutely no current flowing into its negative terminal, so this doesn't really make sense. It's not a voltage divider yet. In order to actually make this a complete and working circuit, I'm also going to need another resistor over here, which I'm going to call RS. And this together is going to form a voltage divider network so that the op-amp can do its magic by adjusting the output voltage in order to control the difference across these terminals. So this here is the non-inverting amplifier circuit, and let's actually go through and analyze it. So remember our steps to follow. So step 1 was check for negative feedback. And I look at this circuit, and clearly we have that. That's part of the discussion that I went through as I was drawing it. So we see negative feedback path through here. So that's all good. We can proceed with further analyzing the circuit. So then step 2 is going to assume that the current that flows in to these terminals, so let's call that IM and IP for the minus and plus terminals. We assume that those currents are equal to 0, so IM is equal to 0, and also IP is equal to 0. And we further assume that the voltage at these terminals is equal. So I'm going to label a voltage here. Let's call this one VP for voltage at the positive terminal, and VM for voltage at the minus terminal. So we also assume Vm is equal to Vp. Now that's only true if the op-amp is in its linear regime, but we'll assume that for now, and then later on we can obviously go and check what values of the input are going to keep us in this linear regime. And I should also label the output voltage. Vout is this voltage here, kind of measured with respect to ground. So it's this plus minus voltage here gives the output voltage. All right, so with these assumptions, I can now go ahead and analyze the circuit. So if there's no current flowing into the positive terminal, so if IP is 0, then there's no voltage drop across the resistor. So no voltage drop across Ri here. And so what that means is that the voltage Vp is just my input voltage. So let's make a note about that. So since Ip is equal to 0, there is no voltage drop on Ri. So therefore, our voltage Vp is equal to our input voltage Vi. So then next step is going to be Kirchhoff's current law at the node labeled Vm. So let's go ahead and do that. So the leftward branch through the RS resistor, current leaving in that direction would be Vm minus 0 divided by RS. And then the current leaving in this direction is going to be Vm minus Vout divided by Rf. And there's no current flowing into the op-amp, so those are the only two branches. that's it, we're done, equal to 0. But we know that the op-amp is going to work to make sure that the voltage at the 2 pins is equal. So what we have is a bit of information. So we know that Vm is equal to Vp, and also we analyze that Vp is equal to our input voltage. So Vp is equal to our input voltage. So we can substitute for Vm. So let's go ahead and do that. So Vm becomes just our input voltage Vi, so I have Vi divided by Rs, plus Vm becomes our input voltage, that's Vi, minus our output voltage divided by Rf is equal to 0. I can simplify this equation a little bit. So the fraction here, because the minus is on the numerator, I can just split it up, and I will get Vi over Rs plus Vi over Rf minus V out over Rf is equal to 0. So bringing the V out to the other side, I will get Vi, which is multiplied by 1 on Rs plus 1 on Rf, is equal to V out over Rf. And I can further rearrange this. I can bring the Rf to the other side, and I'm going to swap left and right because I want to write solving for V out. So swapping sides and writing this out is going to give me Rf multiplied by this, so 1 on Rs plus 1 on Rf times our input voltage Vi. And we can further kind of clean this up. It's nice to put these fractions over a common denominator. So in order to do that, basically multiply each one top and bottom by the other. So what I will get, Rf, this would be Rf plus Rs divided by Rf. That's just putting these fractions over a common denominator, and then I can cancel Rf here. So what I end up with is just Rf plus Rs divided by Rs times Vi, and that's my expression V0. So this is the gain of the non-inverting amplifier. So things to notice here, the non-inverting amplifier preserves the sign of the input, and the gain is given by Rf plus Rs divided by Rs. So in other words, if you know the gain that you're trying to achieve, then you select resistor values such that your gain equals this relationship here. This becomes your design equation for choosing the resistor values for your non-inverting amplifier circuit.